Welcome everyone. It is our pleasure to welcome Professor Shiv Sethi at IMSC for the IMSC Diamond Jubilee Colloquium as a part of our year-long program to celebrate both the completion of 60 years of this institute and 75 years of India's independence. Professor Sethi is a professor of astronomy and astrophysics at the Raman Research Institute, Bengaluru. He got his PhD from Delhi University. After that, he was a postdoctoral fellow at IUCAA, Pune, and then he moved to IAPE, Paris for his second postdoc. Professor Sethi joined HRI India as a faculty. He was there between 1998 and 2004. After that, he moved to RRI, where he is presently a professor. He has a broad research interest ranging from structure formation, reionization era, and cosmological magnetic fields. Today he is going to talk about 21 centimeter cosmology, which is an exciting field that will discover the epoch of reionization. It is also very relevant to this program given India's strong association with the ongoing and upcoming 21 centimeter surveys. Professor Sethi will review the current status of this area of research with highlights of his works in this related field. So without further delay, I'll hand it over to Professor Sethi.
Use this one, right? So everybody can hear me. So yeah, no, it's fine. Can you check that the slide is working? Yeah, works. Okay. So it's my pleasure to be here. I've been here many times, and first time I'm giving a talk here, and this is, I first want to thank the organizers, of course, like Dheeraj and Sayantan, who invited me here. And I mean, I feel privileged to be giving a talk here. And the topic of today's talk would be 21 centimeter cosmology and its prospects and scope. So if one way was to summarize this area of research, one would say that it's theorist paradise. I mean, and that's the one thing I'll try to tell you. And it's an observer's nightmare. I mean, so as much as it is for as good as it for theorists, it's not so much better for the observer, because observation in this area of research, and I'll give you a flavor of both actually, that's the whole idea of my talk, to give you a flavor of what theoretical ideas have been explored here, and what is the evidence that we have scratched so far from analysis of data. So when this topic is often discussed, one rarely talks about the fact that detecting neutral hydrogen itself. So 21 centimeter is a hyperfine line of neutral hydrogen. And this is something we have all read in Feynman lectures. If you haven't read Feynman lecture, he has a full chapter on this. Hyperfine structure of neutral hydrogen. And it's exciting to actually compute quantum mechanically its various properties, like its decay constant and various things. So it comes from spin-spin coupling of electron and proton. It's a highly forbidden line, as they call it. And it's a singlet triplet split actually. So the ground state of the hydrogen atom is split, the singlet at the ground, and then triplet just above it. And the energy split is extremely small. It corresponds to 21 centimeter in terms of wavelength, 1420 megahertz in terms of frequency. This was predicted very late actually. In 1940s, from the point of view of astronomy, this was predicted first. So people first looked at this line from the point of view of astronomy. They didn't look at it from the point of view of doing it in lab experiment. There was a reason for it. So this was done, and this was actually indeed first detected in astronomical setting by Evan and Purcell in the interstellar medium. And it has extremely low transition rates, and that's something that to keep in mind, that if you keep an atom in the excited state of 21 centimeter and wait for it to decay, it takes 1 million years before it decays. Its decay constant is 2 into 10 power minus 15 or so. That's very, very small. And compare it with Lyman alpha decay, which is like 10 to the power 8 or 10 to the power 9 in 1 second. So this is a factor of 10 to the power 23 between the two. So this makes it easier to detect in extremely low density interstellar medium, and that was the whole idea, and that's why it was first detected in interstellar medium. As compared to Earth, it was detected later on Earth actually. Another thing which we are going to use again and again, and this is the hallmark of this astronomy, is that ground state, where there is such a small energy split between the two states, it's easily excited by almost any process. You can two atoms collide, this line can be excited, right? Or by CMB photons, everything excites it so easily because there is such a small energy split between these two levels, and they're connected to the ground state. That's where most of the atoms are all the time. So because of this is the only probe of 21 centimeter, is the only probe of H1 emission in the universe. There's practically hardly any other probe of H1 emission in the universe. Why, you may ask? Hydrogen has so many lines, hydrogen has other lines, why can't they probe them? The reason for that is that Lyman alpha series, of course, like, it's a far more sensitive probe. But the point is, once you excite a Lyman alpha line, you very likely ionize the atom also, because the difference between 10.2 electron volt, what you require to excite Lyman alpha line, and 13.6, not that far. So you can't have astronomical setting like that. So in astronomical setting where you excite the line, very likely will ionize it. So we have no evidence, we have never detected from the neutral medium, that is, the Lyman alpha lines. We only detect 21 centimeter. Lyman alpha line, of course, are a very powerful probe of the ionized medium. When the medium is ionized, there are recombinations, and Lyman alpha and the other Lyman series and Barman series lines are extremely powerful probe of the ionized part. But our aim here is to detect the neutral medium, not the ionized medium. And that's the form in which most of the hydrogen is in the universe. So we'll get a sense. The first map of neutral hydrogen. So the idea is, if you want to detect neutral hydrogen, that's the only practical way for you to do that. There is no way to detect neutral hydrogen apart from this. So the first map of neutral hydrogen, once this line was detected, was made in 1950s, and actually the first time the spiral structure of Milky Way was discerned this way. And the presence of dark matter in spiral galaxies, today the most powerful probe of that remains 21 centimeter line, even today, because 21 centimeter in even our own galaxy, it extends much further than the stars. So you can go much further from the center of the galaxy using H1 as a probe, neutral hydrogen as a probe. So if you want to talk about nature of dark matter, you have to rely upon H1. There are galaxies for which it extends factor of 3 to 4 times more. So it's an extremely good probe of dark matter. It's a very good tracer of star formation in the universe, and there is something called chemical. Sorry?
Dark matter themselves don't emit this line.
No. But the point is, dark matter itself, this is emitted only by neutral hydrogen. But the point is, it's a tracer. If you want to know, for instance, how much dark matter is there, so you take the center of galaxy, and you want to know, you compute what are called the velocities of the tracer. So you can go further about from the galaxies, you can actually get more mass, which is enclosed by the center and this. So by further, you means you can actually get more and more mass, right? So basically, we do not know how big the galactic halo is, because we run out of tracers, right? Because nothing is there. So this is a much better tracer than anything else that we know of. So it's a great tracer for dark matter, but it's also a great tracer for the star formation history. So star formation history is discerned this way. And this has a role to play in cosmological setting also, that it can tell you about cosmological evolution of star formation. And at large redshift, we are in dark right now, what form H1 is. We believe between redshift of 2 and 5, and much of the H1 is probably locked up in what are called damped Lyman alpha clouds, and I'm not going to tell you much about those unless there are questions, which are presumably precursors of spiral galaxies at smaller redshift. But this is debated right now. A lot of evidence is coming that this may be false, actually. That's why I said put presumably, because this might not be true. So this is a history of H1 in individual object. Let's look at the large scale distribution of H1. Right? How is it distributed with respect to the other matter in the universe? So like optical galaxies, it's also a biased manifestation of dark matter. So what actually happens is, we have dark matter and we have visible light. We have baryons, right? So baryons manifest themselves like as optical galaxy, infrared galaxies, but they could also be an H1, 21 centimeter, right? And they're all biased manifestation of dark matter, in the sense that dark matter clusters somehow, and baryons do not cluster in exactly the same way, they cluster differently from dark matter. So these are also, like other forms, biased manifestations of dark matter. One disadvantage here, and that's what I'm going to spend a little bit time on, that it's very difficult to detect it. H1 is very difficult to detect from individual halos, even at local redshift. Forget about far away. We are talking about dreams, about detecting far away, and I'll tell you those dreams, some of them. But you see, I'll also tell you the story of how difficult it has been to detect it in the local universe itself. So it is, but it has advantages. And one of the things is that it is observable in emission, and you can detect it statistically, and I'll try to give you some sense of what this means, statistical detection. H1 maps are three-dimensional, and this is a theme that will run through my talk. There are three-dimensional, they're not two-dimensional. You just don't see it. So you know there are three-dimensional position immediately. And so they are not biased like many other maps are, right? But typically when you look out in the sky, the further you go, the brighter objects you see, and that biases all estimates you make from those brighter objects. So this goes by the name of Malquest bias, and there are many other biases that go with it. So it has certain advantages as well. So now I start the story of detection of H1. First, before getting H1 at large redshift, let's see how difficult it is to detect it. This is the flux density from an individual object. I've just written the formula here, and if you have, I mean, you can stare at it. The one thing that immediately meets your eye is the fact that it's proportional to A to 1. The A to 1 was that the decay constant, which is 10 to the power minus 15. So the line is faint simply because if you put something in excited state, it doesn't decay very often. It decays very seldom. So it's a very, very weak line. And just to give you a number, and you don't have to worry about astronomical number, it is 10 microjansky. Jansky is like a unit of flux density. So if I put 2 into 10 to the power 10 solar masses of H1, the neutral hydrogen, at redshift of 1, now that is more than we have in our own galaxy, like few times more. At redshift of 1, it gives you a flux density of 10 microjansky. 10 microjansky to, so now I have made a comparison next. GMRT, which is the largest telescope, and I'm going to talk about GMRT data because I've worked with it, is the largest telescope in the world at around 610 megahertz, which will probe this line. The line is 1420 megahertz in its rest frame. 610 will give you a redshift of around 1.3. It has a noise per channel of 250 microjansky. So you see how much bigger it is. And even if you increase the collecting area by a factor of 10, which is the next set of experiments, and Dheeraj in his introduction did say India is participating in those next set of experiment called square kilometer array, right? And that is something in which different institutes in India are a part of. India is putting a lot of money into those set of telescopes actually. There are two kinds of SK, and I'll probably have time to talk about it. So even SK can't detect it. Detecting H1 from an individual halo, even at modest redshift, this is redshift of 1, I haven't gone to 50 yet, I'm going to tell you the story about 50. It's not easy. So one thing we do actually, and that is the game that is being played right now, and it's being played for a while, is to statistically detect it. The whole idea about statistical detection of anything is really very simple. If individual halo is too faint to detect, try to detect more than one halo at a time. So one way is, if I know the positions of those objects, I can stack them. I can keep stacking, so flux from any individual object is not detectable, but I add 100 of them, maybe it's detectable then, right? If I know where the flux is, I can keep adding them. That's called stacking. Simple. Very simple way of trying to detect it. Get a sense of the average quantity before we get a sense of the individual object. Cross correlation, and that's a more complicated thing. You take the galaxy position and you cross correlate with the overall density field. This is something which is linear in the H1 brightness or H1 flux. So one can do it. Again, it is akin to stacking because you average over a lot of objects. You average over a lot of objects, so you reduce noise like significantly. I mean, as a ratio of the number of objects over which you average. Square root of the number. Autocorrelation of the redshift intensity, already mentioned it in the last. This is bilinear in flux, it's a harder quantity to measure. This is autocorrelation of redshifted intensity is what we are after in all of ionization studies actually, right? But the point is, it's not easy to detect any of these things. So I'll spend a little more time explaining this very simple idea that you want to detect emission from multiple sources because I can't detect from single source or multiple sources. How do I do that? I have a beam, there are n sources in that beam, or I have a volume which is binding the which contains those n sources. So if I have a statistical measure, suppose a fluctuation of that volume, and the fluctuation delta n is around 0.1, 10%. It has 10% access with respect to the background. So I'm going to detect, if there are 1,000 objects, I'm going to detect 100 of them in my beam. Good, I'm doing better than 1, there are 100. But I have to beat the Poisson noise, which is n to the power half. So for 1,000, the Poisson noise is 33. My signal is 100, so I'm still above Poisson noise, I can detect it. That's a basic idea about statistical detection. And all the measures that we use, every single one of them, uses this concept in one way or the other, right? So various things have been tried, stacking, and this is something that we did quite successfully actually by using GMRT data, and I'm going to show you both simulation as well as data in my next few graphs. So we know the 3D position of a galaxy from optical survey, and we add n objects, and we finally detected it. And this was a redshift of 10. Other is cross correlation, and this was the first time somebody actually reported a measurement. This was in 2010 by Chang et al. Using what's called GBT telescope. That's based in the US. And they also detected this thing. Third is just an idea. This is something but based on my idea with a colleague of mine long ago, that you can autocorrelate the density field, which is called intensity mapping. And this is something which is bilinear and hasn't yet succeeded. This is the future of the field. Here, I'll show you results of a simulation we did in 2011. So here what is done is that a non-large n-body box has been used here to actually reproduce the result of Chang et al. Chang et al. Actually did the cross correlation of the brightness temperature with the density field, and they did it as a function of R, where R is along the line of sight. And we could reproduce those results fairly easily actually, right? But given the fact that the models, like there are many models, one of the hardest thing in astronomy is to associate a mass with the detected quantity. What you detect are fluxes in some, but total masses are not known to us. So connecting it total masses, that's what gives you a difference between different models, model 1, model 2, model 3. So we could do that actually. So in some way it was compatible. The results which was found by Chang et al. Were, you will say, reasonably consistent with an n-body simulation. At that time we also predicted what we might find using GMRT. And this is based on a simulation where we have actually stacked objects, stacked thousands of objects with different noises for the per channel. And we have different models, like you see differences between M's, M11.4, 12, 12.5. And there are different noise. One noise is 6-7 times larger than the other, and the larger noise of course does a worse job, as you can see. In fact, what we got is a noise somewhere between the two. We got 270, 250 roughly. So it was between the two. In a realistic setting we managed to get that. So we argued it's possible to detect it, right? But the next task was to try to detect it. And that is one thing we did try afterwards. I mean, we took GMRT data, and this is based on the first set of data that we took, 48 hours of data, based on 850 sources. So if you take 850 sources and you try to co-add the fluxes from those sources, what I want you to see is how low do we get? We get to a flux density of 2 microjansky. You see, we start with the flux density of 250 microjansky for single channel. First you average the channel, some 9 of them you average. It drops out by a factor of 3, it comes to 70. Then you average over 850 sources, and you gain square root of that factor, and that takes you around here. So we got pretty deep. I mean, this was fairly consistent with theoretical estimates actually from this. So this was pretty successful in the sense that it wasn't a detection, this is not a detection, but this is a very powerful upper limit. So this allowed us to get more data. This was a detection. This was in 2020. This is not flux density, this is noise actually. Okay, noise can be positive and negative, right? Yeah. So no, there is no negative flux density. Here we have a detection. This is 2020. This is 7,500 sources. This is in a slightly different, the y-axis has limits of what's called luminosity. This is a different unit that is used here, right? But it's a clear 5 sigma detection of the signal. And this basically showed that it is possible to use such a technique to detect H1 at reasonable redshifts. I mean, this was possible at redshift of 1.3, and this still is the largest redshift for which H1 has been detected using any technique possible, right? From individual halos, H1 is not detectable to redshift of even greater than 0.2, right? But this technique you can actually use to detect it almost all the way to a redshift of 1.3. This actually allowed us to put a point on the total amount of H1 that there is in the universe, and this is also a plot that you would see always in discussion on 21 centimeter cosmology, that total amount of H1, you may say you haven't really detected any H1 at any redshift, but you have a plot for the total amount of H1. So how did you get this? Wasn't I telling you that H1 is difficult to detect? Yeah, it is difficult to detect in emission. It is not that difficult to detect in absorption using Lyman alpha lines. So from based on that, we can actually cannot say how much H1 is there in an individual halo, but we can actually say what is the cumulative, what is the total amount of H1 in the universe. So that we are able to say, and we are able to put a point here based on the total amount of H1 that we have got at a redshift of 1. So this plot should be kept in mind, because all of our studies that we are going to do with SK in years to come will actually use these plots. So total amount is known to us. The H1 gives you roughly a fraction of the baryons, around 5% to 10% of baryons have collapsed in H1 at that point, and that is what these plots are actually showing to us. Right? They will improve, the error bars will improve. Why the error bars are what they are, I can explain them, but you may not be really interested in knowing what those error bars are and what techniques have been used to actually get them. But these plots will improve, but they haven't changed a lot in last 25 years, so they won't change a lot, very likely. So SDSS, for instance, has put those very small error bars between redshift of 3 and 4. Now I'll come to the grand scheme of cosmology, right? So far I talked about detection of H1. In grand scheme of cosmology, we looked at, of course, cumulative effects only. We don't look at individual objects, right? But my point was to convince you so far that individually they are difficult to get, right? So we have to use statistical techniques which are completely consistent with what cosmologists are going to try. For cosmologists to try out anything, we first look at the grand scheme of things, right? There is Big Bang, right? This is the Big Bang, right? And after Big Bang, you have, this is Big Bang, then is a recombination. This is called the recombination era. This happens roughly 300,000 years after the Big Bang. After that, the medium is neutral, and the game we are playing actually extends all the way from here to here. What I was telling you about was roughly here, which is redshift of 0 to redshift of few actually. But we should look at it the wrong way. We look at it from the other way. 300,000 years, neutral medium afterwards, then first structures start forming, and these are the first structures forming. Finally, they reionize the entire medium by around 1 billion years. And it is what is called epoch of reionization, in which there is a lot of interest right now. Is basically a study from here to here. So roughly there are 3 eras here, which I should try to mark. So roughly around here to here, there is no clear demarcation. Is what's called epoch of reionization. That's when the first stuff starts forming, and then they reionize the medium. So from roughly here to here is reionization. Just before that, when the first start forming, but the ionized fraction in the medium is tiny. That era is called cosmic dawn. The cosmic dawn has just happened, as if. And before that, there is this entire era from redshift of roughly 1000 to 50. This is called pre-reionization era. This has happened before reionization has happened, and all of these eras leave detectable signatures for us to find, and they are actually more and more powerful probe of some mysteries of cosmology. So this is the way reionization was studied, and I'll just give you a very brief overview of that. I'll go to the main theme of the topic, that you'd actually try to detect this using what's called Gunn-Peterson test, and this was by looking at a quasar at different redshift and looking on the blueward side that there is an absorption, and on the redward side there is no absorption, which suggests that there is H1 in the intergalactic medium which is absorbing it. And based on this, one could actually find that the reionization, the universe is becoming neutral at a redshift maybe around 6.5. But this is such a powerful probe that even if you have tiny amount of hydrogen in the medium, it still causes an absorption trough. So this was only a partial indication. CMB is another probe of the same thing. So CMB, you must have seen these plots. I like this because they have put together. This is temperature correlation. This is temperature E-mode cross correlation, polarization cross correlation. This is autocorrelation of polarization. This is autocorrelation of the B-mode polarization with itself. These are foregrounds and various things. The point is, this part, L between 2 to 10, is a powerful probe of the reionization era. So if reionization was not there, these things will keep falling. So reionization makes a difference of around factor of 10 here. Reionization, so what actually happens with CMB photons is around 6 to 7% of the CMB photons, they scatter again. So they are coming from last scattering surface, and they scatter again at a redshift of around 8 or 9. And this is what we are actually seeing here in the CMB powered spectra. So this has of course been measured, and this is just a plot from Planck era, a posterior probability of the optical depth to the reionization surface. And you can actually see that you have found an optical depth which is around 0.05, 0.06, and this corresponds to a reionization redshift of around 7 or so, right? So this is the current story, and this is what people have found Gunn-Peterson rough on the one side, which is telling you the universe is probably becoming neutral between 5.8 and 6.2. And Planck results, which are suggesting that reionization probably happened between 6.5 and 7.5. These are complementary probe, one based on neutral hydrogen, another based on ionized medium. Now we do not know if these two are in agreement. They are mostly in agreement, because the point is the gap between them has decreased over a period of time. Right? Earlier the gap was large with WMAP data. And the story is that if you can directly detect neutral hydrogen at high redshift, that will provide a more direct probe. So for redshifted H1 line, that is doing radio astronomy in a frequency range between 100 and 250 megahertz. So story will change, go from CMB, which is already done and dusted, right, to direct detection of hydrogen at high redshifts, directly detecting H1 and doing the experiment between 100 and 250 megahertz. So here, now again I'll change tack. So this is what we wanted. How is it that such a story? So I told you there is pre-reionization era, before reionization starts. It's cosmic dawn when it just starts. And then what is called epoch of reionization when it finishes, right? So this is a story of those 3 eras, and that's what I'm going to actually tell you, right, from theoretical perspective. So this is a plot of recombination of the permeable plasma. So universe was totally ionized at redshift of around 1100. It recombined, and the level of ionized fraction fell to 1 part in 10 power 4. Many people believe, okay, so what? 1 part in 10 to the power 4 should be similar to 1 part in 10 power 5 to 1 part in 10 power 3, because as far as CMB is concerned, the photons do not scatter again after when it falls to roughly 1/10. So there is this long tail of ionization fraction. Does it have an effect on any observables we may have? It does have, actually, because I mean it shows when Edge's result came, when it basically suggested that if the ionized fraction was 10 power minus 5, those results will radically change. What I have plotted here also is I have plotted just these three models where the reionized fractions can actually increase. Right from here, this will not violate CMB results most of the time, but so far from whatever observations we have done, it's very difficult to tell the difference between this and this, right? So if you want to tell the difference between this plot and this plot, which is off by orders of magnitude, you'll have to know your physics well in pre-reionization era and the era of cosmic dawn. So that is what we are leading to. The difference between these two plots are not known to us yet, because CMB tells you roughly what happens here, right? And there are observations at late redshifts which gives us partial information. But information that we need about the difference between these two hasn't happened yet, but will happen in years to come, and I'll try to convince you that we may be able to get there. This is a story of thermal decoupling, and many people, when they look at this, they don't realize there is decoupling. The decoupling is associated with redshift of 1000. That decoupling is only of a photon scattering of an electron again. That is not thermal decoupling. Thermal decoupling is an era. They are thermally coupled. That means CMB and matter continue to have the same temperature for almost redshift of 100 actually. Then they decouple again. And matter cools faster, roughly 1 by a square. It falls adiabatically. And CMB falls as 1 over a. Is there evidence of this? That matter was cooler than CMB at redshift of 100 to 20? No, we don't have evidence of it. What evidence can we find? Again, to find this evidence, we'll have to go back to those eras. And there is only one way to probe those eras. Like that is either pre-reionization or the transition between reionization, pre-reionization and cosmic dawn. So my idea of showing these plots to you is that these plots have been done based on physics we understand at an earlier time for which we have evidence. But we do not have evidence for late time, right? So now I look at what the H1 signal is. You may say, oh, there is H1 out there, so it will emit and you would see H1 because it's there. Not really, because there is CMB which is falling from behind, right? So if CMB is coming from behind and H1 is in front of it, right? So if CMB thermalizes with H1, you'll see nothing. It is clear, it's a pure thermodynamical principle. That H1 simply because it's there doesn't mean you will see it. You will not see it. That will depend on the properties of what else is happening. And I'll give you a rough sketch of what really happens. So this is basically, it's a complicated relation. You see, this is the delta TB is the difference of brightness temperature of H1 from CMB. And this is the only observable quantity. If this difference is 0, you see nothing. There could be a lot of H1 out there, but you don't see it. because it thermalizes with CMB. So this is, of course, like when this is equal, Ts is equal to this is called the spin temperature. When the excitation temperature, which is called spin temperature in this case, is equal, this goes to 0. So this is around, the number you have to keep in mind is around 26 millikelvin, well, 30 millikelvin. That's the kind of number we are talking about. The brightness measurable for us from that era is around 30 millikelvin. We'll compare it with other numbers as I go along. So between redshift of 1000 and 100, this is indeed 0, because the spin temperature is CMB temperature. So the signal starts out at 0. There is so much more neutral hydrogen out there between redshift of 100 and 1000, but we don't see it. Why? Because it thermalizes with CMB. Later on, this thermal coupling breaks. Why does it break? Because matter cools faster than CMB. That's what I was saying in the last view graph. And we have a detectable signature of that here. This is called the pre-reionization signal. In the redshift range between 20 and 100, you would see that this brightness temperature difference is negative because matter temperature is below CMB temperature. As cosmic dawn happens, there are other ways to couple the two ground states of the hydrogen, neutral hydrogen. And this causes a lot of other things. It can cause another absorption trough. And that is what is interesting, and that is presumably what was seen in the so-called edges result. Then comes the epoch of reionization. X-ray heating, if there is X-ray in the medium, it causes heating, and such that the spin temperature becomes greater than the CMB temperature, and you would see it in emission. All of this information you would find in this single plot. So you start from here at very high redshift, corresponds to a very small frequency. This initially starts at 0, like I convinced you. Then it goes into absorption. Why does it go in absorption? Because matter is cooler than CMB. It's absorption, and you can read out this number, some roughly minus 40. Then it goes again towards 0. Why does it go again towards 0? Because the coupling of matter with CMB, coupling of matter with H1, spin temperature weakens. Then there's another absorption trough. Why does it happen? This is what's called Lyman alpha coupling. That can, and I'll not go into not explain it, but I can explain it to anybody who's interested. Can go into another absorption trough. Finally, first time you see it in emission, right? That is at a much later redshift, right? This redshift will correspond to between 10 and 15, and then finally it tapers off, and everything becomes ionized finally. So the signal goes to 0. This is what we expect. 2 absorption troughs, 1 emission. Exciting. And this comes from pre-reionization era, like I said. This comes from what is called cosmic dawn, and this comes from what's called epoch of reionization. So we have clear signatures of the 3 epochs. Of course, you may ask which one of them is unique, and which one of them depends on the model that you have constructed, because you see people are clever with constructing models. So I'll tell you, this one is unique. This one will happen, period. There is no way you can actually get rid of it, because we know our cosmological parameters too well. This is model dependent, so is this. So there is a lot of modeling that goes into these two. And we do a lot of models to find out how deep this would be or how shallow this would be. Would it even exist? It may not even exist under certain cases, right? And this can change too. But in fact, I can construct a model where this entire era cannot be seen at all. But let's not go that far, actually. People are spending a lot of money in making instruments, you see. If we went that far, then all those experiments will fail. So what I've talked about is the global H1. So you take the sky and you average the sky and you look at in any direction. So direction is not important. You can pick any direction, and you look at the difference between CMB and the brightness temperature of the neutral hydrogen. That's what you actually see. And that's what I've plotted. It's called the global H1 signal. But you see, what we are interested in is a double difference, and that's what I've shown here, a double delta of delta. So this first delta, the larger delta, is the difference between CMB temperature and the brightness temperature of H1. The other delta is the difference of this between two different spatial points. And that's why I put it as a function of k, which is the Fourier mode, or could be x, the spatial mode. So this is the quantity we are interested in, actually, the fluctuating component of the H1 signal. How does a signal change from one position to another? These are quantities we are always after. This is what we are after in CMB, right? CMB is what we have detected all these things in CMB. So, but here the origin is a little more complicated. What are the sources of the inhomogeneities of the H1 signal? It could be ionization inhomogeneities. The universe is ionized. One ionized patch is different from another ionized patch. And this can give rise to statistical quantities like power spectrum, which is different from 0. You have kinetic temperature and spin temperature inhomogeneities. And both of them lead to interesting consequences. And if you go to higher redshift, you have density inhomogeneities also. The gas has density inhomogeneities which you can potentially probe. So last two, in fact, probe in some way the density inhomogeneities probe pre-reionization era. Spin temperature inhomogeneities probe the cosmic dawn era and a part of kinetic temperature inhomogeneities. And ionization inhomogeneities and kinetic temperature, mix of the two, probe the last part, which is called the epoch of reionization. So you can actually demarcate it like this based on what is the nature of inhomogeneities. This is a quantity all of us want to study, the power spectrum of the observed field. And I've just written it out in a formal sense of what this quantity is. I have just tried to summarize what I have already said, that density inhomogeneities are masked by other inhomogeneities, and we are interested in a redshift range between 8 and 25, and that gives you a rough sense of where the SK will operate. SK will operate roughly in this range. Spin temperature inhomogeneities early times, kinetic temperature later on, and ionization inhomogeneities dominate at the end. Density inhomogeneities probably play no role at all, and what I'll show, convince you of some of these things, is this complicated plot which I've taken from one of my own paper. This is the expected H1 signal. I have taken one scale. So I've taken K of around 1.1 megaparsec inverse. And what I've done is I've plotted it as a function of redshift. How many different models are there? Please just see for yourself, just soak it in. Right? All of this is possible. Whatever I've plotted here is possible. And we are not able to tell the difference between any of these two, except if edges result, there was this detection which was reported. If this was true, then we expect this. One of those things would be picked out, if that was true. If that is not true, none of them can be picked out. So this is basically how well you couple Lyman alpha with the rest of the matter. So if the Lyman alpha photons are fewer, 0.1, the signal is negligible. As you increase the coupling of Lyman alpha, the signal becomes larger and larger, spanning a range from 10 to the power minus 2 millikelvin square to roughly 100 millikelvin square. It can actually span that entire range, right? But this would be at a redshift of 20, if that redshift of 20 can actually be probed. So a complication in this, there are 3 peaks also if you actually pay attention to it. The third peak I have not shown. One is here, one is here, and one is here. So you can actually have 3 peaks corresponding to one coupling, the second coupling, and the third coupling within the range of these complicated models. So point here is a lot of models are possible, and experiments have to be able to distinguish between them. So far we haven't really succeeded. There are some observations at this end which I will actually show to you a little later. Now I'll come to the pristine part of the signal. So like I said, the pre-reionization signal is pristine. I mean, this is like where reionization has not contaminated anything, right? Reionization contaminates everything. It makes the signal very difficult. The density inhomogeneity is our pristine signal, because that is where our initial condition of the universe is in some way. But that initial condition of the universe is gone because of all of these complicated processes. But to get to reionization, pre-reionization, which is this plot, you have to get here. What is the frequency here? From 15 megahertz. So it might just look like a number to everybody. 15 megahertz, you can get to 50, so why not 15? The point is, and that is where I started out my talk. I said, like, it's a theorist paradise. A theorist like take 2 minutes to say, detected 15 megahertz. And experimentalist, and to give you a sense again on what I have said so far, we struggle to do it at 610 megahertz. 610 megahertz is infinitely easier to do things at than 15 megahertz. Why? And I'll come to some of those reasons. Almost everything, starting from foregrounds to ionosphere and everything. From Earth-based, we can't even do this kind of experiments at 15 megahertz. So yes, it is an extremely clean signal of the thermal and ionization history of the universe. So clean that everybody, when people look at it, they say, wow, this is it. Like theorists, like actually, they're very happy looking at this. But fact of the matter is, it's not easy to do it, but we should speculate because it might become possible in years to come. But this is very good signal in some way. Global and fluctuating component, the peak signal is around 50 millikelvin, that you could see actually. That was the trough. And the fluctuating component is multiplied by the density contrast of that, and density contrast is around 0.1 for scales of interest. So the effective signature is around 5 millikelvin. Okay, so can we detect 5 millikelvin? That is the aim here, right? At 15 megahertz roughly, in the range between 15 to maybe 30 megahertz. What is very important here and what is very, very interesting here is what it means theoretically. Theoretically, it's actually a probe of linear perturbations at scale smaller than accessible to any other cosmological observation. Now, this is a story which is not often told. What cosmological observations, what are the smallest scale we have actually probed using cosmological observation, which is a reliable probe? Well, I mean, we have gone to reasonably small scales, like a few in megaparsec inverse. But the most reliable probe comes from CMB, and that's around 0.1. So 0.1 megaparsec inverse is the smallest scale we have gone to. This will take you to a factor of 40, at least 40 below that. And that's where the initial condition in the universe might be. And from a particle physics perspective, and this is what particle physicists are so keen on, this kind of a signal, is because you want to detect neutrino mass. It hasn't been detected yet. It's out there, but it hasn't been detected. So you want to detect neutrino mass, you have to go to very small scales. There is no other way around it. And if you want to detect between what's called normal and inverted hierarchy, I'm not going into details of what that actually means. You have to be able to go to an observation such as this. There is no way we are going to be able to do it using any other cosmological probe. One has devised many, many probes. I mean, I myself been involved in studying many of them, but it's not possible. This one is clean, this is beautiful, but it's very difficult. I have to tell you that part about very difficult. So this is from one of our recent papers when we also become very speculative. And basically like for two inflationary models, we introduced some feature in the inflationary power spectrum, initial power spectrum, and we study the viability of whether we can actually, what would the H1 signal look like for redshift of 27 and redshift of 50. And these are the plots for two different models. And of course, we argued that it might be possible to actually detect this using a radio telescope from moon, which is being proposed right now. But whether I can tell the difference between this and this still remains. But you can see the difference here, the neat part here is the difference between these two models is large. It's almost order of magnitude. So we may be able to actually probe such a dip from a primordial initial condition. Okay. Now we come to challenges. I've kept telling you about challenges, so now we come to challenges, the part of challenges. How long do I have? I have around 20 minutes. 10 to 15 minutes. 15 minutes. So, first of all, the brightness temperature is around 3 to 10 millikelvin. I've convinced you of that. I've showed you plenty of plots, right? 3 to 10 millikelvin. That's a number, keep in mind. Foregrounds. What about foreground? What about other stuff? Therefore, 3 to 4 orders of magnitude larger than that. Okay, so that's like, really? 3 to 4 orders of magnitude larger than the 3 millikelvin or 10 millikelvin we are going to have in the frequencies range of interest. So, that's a challenge. And you may say, well, then why are you talking about it? If something else is brighter than what your signal is, right, why are you talking about it? Can you ever detect it using any means? Was it possible in CMB, for instance? People compare it with CMB observations all the time. In CMB, it's not possible. CMB signature signal is in 2 dimension on the sky itself. And we can detect it because CMB dominates the signal at 100 gigahertz. Between roughly 60 gigahertz to roughly 300 gigahertz, CMB signal dominates the foregrounds actually, right? Totally. I mean, totally in the sense foreground's contamination is less than 20% even at 300. It's less than 10% at 150 gigahertz. So sure, one can do that. It must dominate. Here it's 4 orders of magnitude. Can we detect it? We can actually. The point is, this signal, like I said some time ago, it's in 3 dimension. It's not in 2 dimension. This signal is in 3 dimension because it's a line. So once line radiation, it's a line radiation, that means once I detect a frequency, I know the frequency of emitter because frequency of emitter was fixed. It was not a continuum line like CMB. So the entire signal is in 3 dimension. It's not in 2 dimension. So in principle, we can detect it. Here I've given you some numbers for even the global experiment like Edge's result, which I did not talk about today. Also, you need system stability for hundreds of hours to detect the signal, and I'll comment on the system stability in coming view graphs. In principle, the fluctuating component can be distinguished from foregrounds along the line of sight. H1 signal, because it's a line, behaves like a line. I mean, even though it's in correlation space, it's not entirely straightforward, while foreground is continuum. So in principle, and I'll show you some very straightforward method by which you can actually isolate foreground from the what is called the EUR window, which is dominated by the signal. The other method is to actually model all the foregrounds and subtract them. So this is a brief review of all that is being planned actually. So there are two kinds of experiment. One are called global EUR experiment. They want to measure the global signal, right? And the global signal is a single dish. You go out in the field and you try to detect the global signal. And Edges did report a signal here. The first report of a signal was like a few years ago, 3-4 years ago, and then it is in 70 and 90 megahertz in the redshift. If it was H1, redshifted H1 between 15 and 90 of an absorption feature of nearly 500 millikelvin. The trough was too big actually, so I'll not go into interpretation of that. So there are other experiments, one where I work in Asaras, which has been ongoing there. And these antennas, like they work in the range of 50 to 200 megahertz. Then there are ongoing and future radio interferometers, like there is GMRT, there is MWA, this is called Murchison Wide Field Array, data with which I have worked, and I'll show you some results of that. LOFAR, HERA is ongoing right now, and so is LOFAR, right? And they are also in a frequency range between 100 and 1000 megahertz. There is SKLO, that is something in which RRI is also involved, and actually Indian community is involved, right? Between 50 and 300 megahertz, right? And SK mid also plenty of groups in India are working on SK mid data also. That's between 700 and 2000 megahertz. So these are upcoming, these are 2026. Then if you want to go to even smaller frequencies, 50 megahertz, like it pretty much defines the limit for you to go to study ionosphere. You have to go to smaller frequencies, you have to go to moon. And missions have been proposed already that you can go to other side of the moon called far side and try to operate in the frequency range between 10 and 30 megahertz. And that is where what I talked about, for instance, I said like we proposed something, and there are many other proposals, neutrino mass, pre-ionization signal. That is going to be the scope of such experiments. So these are foregrounds. They have just pictorially showed that you have UR signal of 5 millikelvin, and extragalactic foreground 0.8, galactic around 2 Kelvin. So they are pretty large actually. And this is like just pictorially they actually show you. I have already given you these numbers. So again, these are view graphs. I'll just go through very quickly. So when you use a radio interferometer, you can actually detect EOR in theory. So what you have is an interferometer. You have two telescopes which are actually trying to look at the signal at the same time. And they probe two Fourier modes on the sky. And then you have one Fourier mode along the line of sight, which basically comes from the frequency, because you measure the frequency. And in principle, you can relate the parameters of the interferometer. And these are parameters of the interferometers. Right? These are called baselines. And these are called the delay parameter. You can relate them to Fourier modes of the signal, and that's why I just showed you this. So the Fourier modes, there are 3 Fourier modes of a signal in 3 dimensions, and they can be related to the baselines and the delays, the frequency channel width of the experiment. So it's all entirely possible, and that is a technique we actually use. And this can be actually used to non-parametrically isolate for foreground from the signal. And this is important because this is what theories do. You see, people who are observers, they are actually mostly dealing with even harder issues like calibrating an instrument. Theories actually try to at least isolate foregrounds from the signal. You have to prove that it's possible. Otherwise, this entire experiment or set of experiments are meaningless actually. Right? And there is billions of dollars being spent on it. So one has to prove that this is possible. So I've just given you a very simple exercise of what happens when you have a point source. And you can actually extract a point source. And in the correlation space, you can extract a point source from the region where there is no point source. It's done in 3 dimensions, and I'll show you this plot actually, which is much more meaningful. So this is actually a contour plot of the signal of a set of point sources. I have just like 100 point sources here. So this is done in the space. K perpendicular is the Fourier space along the plane of the sky. K parallel is along the line of sight. And what you are able to do is to isolate foregrounds in this small region, which is called a wedge. This region is roughly clean of all the foregrounds. So in principle, you can actually detect the UR signal here. Isolation happens here almost 9 orders of magnitude. I'll show you that with data, it's entirely possible to do the same actually. But 9 orders of magnitude may not be enough. We need more than that. Okay. So it is possible, so the first proof of concept exists that foregrounds can be separated or isolated from the H1 signal. You see, if you can't prove that, you might as well go home. Whether we can do it as well as we require, we haven't proved that yet, but it's at least possible in principle. H1 signal looks like this. I mean, it looks the opposite, right? You see, you may look at foreground and say, okay, foregrounds are all here. So H1 signal is like this. So you see, all of it is lost. This part is all lost in foreground. This part is detectable because foregrounds will clean this up, right? So this part is detectable for us. So we may be able to. But you may ask, is it a unique prediction of H1 signal? No, it's not a unique prediction. I could give you models where this will shift up or it can shift to the right and various things. But this is just one model of H1 signal where H1 signal could actually be exactly where it shouldn't be. Because we want to detect it and foregrounds will kill that signal. So here I have, again, very briefly given different methods of trying to detect epoch of reionization. So again, there are instruments which are imaging instruments like LOFAR, MWA. A region is tracked and imaged in 3D, and then its power spectrum is measured. So foregrounds are either subtracted or isolated in Fourier space. We always isolate. We never can subtract. There is no way we can subtract foreground. That's an impossibility. People have discussed it for a long time. It's not possible. So other approaches include Fourier-based methods using four-point modeling, and that is something that I worked with. So that's why I've just mentioned it here. So there are at least 25 techniques which are being used right now in the literature for at various parts of the pipeline. We all write our own pipelines and we introduce novelties in different parts of the pipeline to see if the signal, if you make a difference actually to the analysis of data. And we all report some improvement, small improvement over the other in most cases. But so far there is no convergence here. Drift scan is one of the things we worked with a lot actually. And this is something that, because of system stability, here you keep the instrument is unstable. So you keep, our idea is keep the instrument there, keep looking at the sky at the same point, let the sky drift. Let's see if I can analyze that data and do better than that. And there are certain advantages to doing this, right? Only problem is that when you track a region, you can take a clean region and track it. That's good. But when you are drifting, you do not have that in control. Dirty regions will come into your field of view. That's beyond you. That you can't control. So there is a give and take here. Somewhere you gain, somewhere you lose. So we have actually analyzed this a lot. Like we looked at it theoretically, and then we looked at it experimentally. We looked at MWA data that we ourselves have got and analyzed it. This is our analysis of the data. So if you actually look at so this is again MW, so you may ask what are these stripes? These are because of the instrumental flaw in MWA. So this is a telescope which is based in Australia. It's called Murchison Wide Field Array. This is in Western Australia, far away from all sources of interference. So it's actually a very, very clean site, right? So, but there is an instrumental flaw in that there are some missing frequency channels which cause this striation, like you can see them here actually. So this is because of that, it's not because of anything else. When I showed you simulation, these were not there. But even so, you can see this looks pretty much like what I showed you, right? You have foregrounds which have been isolated to the bottom of the curve, and you have these clean regions. These blue regions are the cleaner. You can see this range goes from 10 to the power 7 to 10 power 16, 9 orders of magnitude, right? Plotted 9 orders of magnitude there also. Here also I plotted 9 orders of magnitude to just draw your attention to the fact that there are 9 orders of magnitude in this plot. And this is not 120 minutes, this is 120 minutes of drift, but this is actually data of multiplied by 10 of that. So this is 2 hours multiplied by 10, so this is almost 20 hours of data that has been used to plot this. And this is one polarization, that is another polarization. And they look more or less the same, but there are differences, right? Some regions are pretty blue, pretty clean, and we can isolate them, and you can show that those results are pretty good. Others less so, right? Part of the reason is because of these missing channels which has bothered us, which has forced us to throw away almost 20-30% of data. But the technique as a concept works. For 20 hours of data, if I had plotted, we had 55 hours of data. Almost 30 hours was usable. Then a galaxy came into our view, so it was completely useless after that. So we could use some part of the data and publish results which showed that this isolation is possible. So what I showed you as a theoretical possibility is possible with data, but we require to go almost at least few more orders of magnitude. That is not possible so far. So here is a plot of another compilation. Somebody has compiled with MWA, right? So we were part of some of these collaborations because we are part of MWA. And then paper was a predecessor to HERA. It's no longer working now. LOFAR is still working. And GMRT, of course, this was so long ago. So here is a compilation of current constraints from the EOR, and which I have just shown here. And you can actually see that you can read off these numbers, 10 to the power 3 to 10 to the power 5. And the number increases steadily as you go to larger redshift because you're going to smaller frequency. And it is way harder to do things at 120 megahertz as compared to 170 megahertz. So this is the difference between 120 is here, 170 is here, and you can see that everything is bigger there. It's way harder. I mean, you may think like this is just a small range, but it's not, right? Your ionosphere is a mess, right, as you go to smaller frequencies, and so are your foregrounds. And your instruments just do not work so well anywhere in the world, even if you have at sites which are completely clean. So this is something, it's a recent compilation, it's probably within the last 1 year, and these compilation, different people give different compilation of results, right? So you can see if these are theoretical signals, like these are 3 models, theoretical models that are plotted here for comparison for different scales. We are still 2 orders of magnitude far away from it. So we are not really close to detecting this signal, right? We are still struggling to get where we need to be. And there is a lot of money here which has gone in. So clearly, I mean, HERA is the largest telescope currently operational. It's a drift scan instrument. Like it works the same way, like as I described when we worked with MWA. Paper was a drift scan instrument, no longer working. MWA can work in both modes, right? GMRT, no one has tried using it in drift scan, right? I mean, I've discussed it with people, but never got around to it. Nor has LOFAR. And I've talked to people in LOFAR, they don't believe it will actually gain much, right? Given the fact that they are the sites where they work are not so great anyway. So this is where, with this last few graphs, I will end my talk. So again, scope and prospects. So first, scope. It allows probe of the universe in the redshift range between 0 to 100. Nothing comes close to it. When you actually talk about various different probes, like a single probe which can actually take you from 0 to 100 and give exciting astronomy output in that entire range is quite remarkable, in fact. So going from dark matter, probe of dark matter, to probe of star formation history and evolution of star formation, to probe of dark energy, which is one of the aims of SK mid, for instance, with H1, and then going to reionization era, that is looking at the first stars and galaxies, right, in the universe, and then going to cosmic dawn and probing the ionization and thermal history, and then going to even further back, pre-reionization signal, and looking at pristine signal on scales where we have no hope of probing any other way. So it has tremendous scope. There is no question about the fact that this area of research has tremendous scope, right, when you view it in the light of these. But from the point of view of an observer, and when I stand here to give this talk, I realize that, I mean, and I was telling Dheeraj before I started my talk that, you see, this is something I'm moving out of this area of research, not getting into. And so I thought this would be an opportunity for me to give this talk. And one of the reasons I'm moving out of this is because of this second reason. Because I played with data for many years. And when I played with data, I realized that we are far away from where we need to be. We are not close to that. Maybe I gave up too early. I mean, as some people tell me that, you should have continued with data, right? After all, their exciting data is going to come, and we are a part of SK, so maybe I'll get back in. But point is, at the current time, our best hope on UR signal for just UR signal, we are still orders of magnitude away from where we need to be, right? And this is not for the amount of data, because one question none of you asked, and you should have asked, how much data is plotted there in those view graphs that I showed you? I mean, it doesn't matter the amount of data, because after 50 hours or so, we all stagnate. We can't integrate and reduce noise. And this is the story of all instruments so far. So new instruments are being built. They may actually do what other instruments have not done, and young people may actually want to go and do it. And this is the story of this area of research. So I'll stop now. Thank you very much.
Thank you, Professor Sethi, for this nice overview of both from theory and observational perspective of 21 centimeter cosmology. Now the floor is open for questions. Please raise your hand if you have any questions. Okay.
Can I ask? When you said it can probe dark matter questions, can you tell something about the mass of the dark matter, potential mass of the dark matter candidate?
And the neutrino. So you see, there are two kind of dark matters, right? One
But I thought neutrino is already ruled out as dark matter candidate.
No, you see, so let me finish.
Yes.
So the dominant form of dark matter is what's called cold dark matter.
Yes.
Right?
Oh.
That much is clear. But there is a subdominant component of dark matter which is coming from the neutrinos, right?
Oh, possible, yeah.
Not see, if you believe in particle physics, the hierarchy. So the point is the minimum mass of neutrino is either 0.05 electron volt for the
Right.
normal hierarchy, or it is 0.1 which is inverted hierarchy, right? So either of these two possibilities are there. So 0.1 is a subdominant component of dark matter. It's not the dominant component of dark matter.
But it can be a new thing, something like ultralight dark matter.
It is
something like 10 power minus 22 electron volt.
That is right. So by the way, that 10 to the power minus 22 electron volt,
Yes.
what is called ultralight axions, those behave more like cold dark matter actually.
Right.
Right? So if it comes to a probe of cold dark matter, so cold dark matter is pretty well studied using CMB observations, right? Of course, its nature might be different below a certain scale.
Yes.
The idea here is that I can probe scales much smaller than CMB scales.
Right.
So if dark matter is behaving, for instance, ultralight axions, I've worked on those things. So those actually give rise to a decrement in power below a scale.
Right.
And the scale depends on the mass of the ultralight axion. So if the ultralight axion is around 10 to the power minus 23, you get discernible decrement in power at k of 1. But this will go to k of 10, so it is possible.
Okay.
So it can do what you're suggesting.
Right.
But its real contribution would be, I mean, from the point of view of a unique contribution, right, would be that it can actually detect those neutrinos very likely, which are out there, right? Whether it can distinguish between normal and inverted hierarchy, and that's very difficult. Because the difference between them is one neutrino of 0.1 or two neutrinos of 0.05 free streaming into the medium. Cosmologically, the difference between the two is at the level of less than 1%. That we are not sure of. But neutrino it might detect.
Because for that, there are now experiments for distinguishing between these two, inverted and normal. Even what you may call lab experiments, the reactor kind of experiments are there. So hopefully in another 10 to 15 years, the data might be collected to resolve that issue to some extent.
Yes.
But I'm more worried about the cosmological things. So I'm looking at potential use for better understanding dark matter candidates themselves.
Absolutely. So the whole point is once I go to almost 1.5 orders of magnitude in scales. So we have plenty of dark matter models whose predictions are totally different from the cold dark matter particle. So I worked on some of those things, like ultralight axion is one of them. There are a whole range of models like WDM, warm dark matter particle. So they lead to a decrement in power, and this kind of an experiment, like this kind of observation, will tell you about that also.
Okay.
I didn't emphasize that point actually.
Okay.
Yeah, but sure.
I have another naive question.
Please.
See, there is a mass limit for photon, light itself.
Yes.
Which is by geomagnetic analysis, etc.
Yes.
It says something like this, less than 10 power minus 18 electron volt.
Yes.
Now, can this thing put a better bound
Yes.
on the mass of the photons?
10 to the power minus 18, you see, I think we discussed.
Less than that. We don't know anything beyond that.
See, the 10 to the power minus 18, so a photon, so the point is, let's say that it's in the vacuum state, right? And it has a mass of 10 to the power minus 18. Then it can behave like a scalar field, a boson, right? Then its prediction might be very similar to ultralight axions.
Excel.
And 18 is difficult to probe. 18 might be, these experiments might be needed. So you see, I remember numbers, 10 to the power minus 22 you can go.
Right.
Of k of 0.5 or so. Yeah, this experiment might be able to say, that maybe you can chat about it. For 10 to the power minus 18, if you are able to go to 10 to the power minus 18, I'll have to check that scale actually. Often I don't remember. because 10 to the power 18 always seemed too large to me for ULA mass. We never go that large actually. We go between 10 power minus 25, 24 and 22 actually, because that is where the exciting cosmological scales come.
Okay.
10 power minus 18 would take you to even smaller scales, so you might need these kind of experiments. Interesting point actually.
Okay, thank you.
Yeah, we can discuss it.
Okay.
I mean,
In one of your slides, you mentioned about this inflation and signals of inflation. So I didn't quite get it. So can you use these H1 information to get information about the inflationary phase?
absolutely. Okay. I mean, I'll just go back this one, right?
Okay.
So the idea is the following, that the fluctuating component of the H1 signal that we see, it's basically the initial power spectrum multiplied by what's called transfer function, which is all the relevant physics that happen, neutrinos, all those things, cold dark matter, baryons, photons, they all play a role later on, right? But is it a probe of the initial condition? That's the point actually. So as far as inflation is concerned, the real issue is it a probe of initial condition? Absolutely, it's a probe of the initial condition, right? Generally, like when we talk about probe of initial condition, we are talking about very large scales, right? But in fact, it is possible to probe at very small scales also, right? If the signature is not easily mimicked by something else, right? Now, such a signature is unlikely to be mimicked by something else. See, I can actually have transfer function from other things, but it will not mimic a dip and a rise like this. That is the whole idea of this work.
And there are also different models of inflation. People don't have an agreement on what is going on. So can these signals be used to rule out something, or?
Yes.
Okay.
So the whole point is these signals, again, it's an issue really of going to smaller scales. When you act, so you see what happens is CMB is a very good probe of inflation already. And the reason is because we have, from CMB observations, we have a probe from k equal to 10 power minus 4 megaparsec inverse to roughly 0.1 megaparsec inverse. This is 3 orders of magnitude in k. So the baseline is large, right? We are talking about increasing the baseline by another 2 orders of magnitude. So absolutely, the whole point is it would be a much better probe of any inflationary models. But I'm sure inflation, there are so many models, whether it can actually pinpoint the right one, that question I don't believe anybody can really answer.
Also, there is this discussion about whether there is a preheating phase versus reheating and all. So will these kind of experiments tell something about that phase more?
Not preheating, probably reheating. So the preheating actually does happen, so in inflation. So there are 2 probes. One is at large scale. What was the initial condition when the first scale left the horizon? The scope of that is CMB at very large scales, L between 2 and 10, and that's what people talk about. The reheating happens towards the end. Yes, this could be a probe of the reheating, yes, absolutely. Because towards the end is where the small scales leave. So this can actually potentially say something about it, but I haven't worked on it, so I can't give a more specific answer to this question. But yeah, it's going to be sensitive. Right. You have improved your baseline by 2 orders of magnitude. That's what you have achieved.
Thank you.
Preheating also is dependent on the model as well, right? So that is also another problem. But by the way, what are these different levels that are here, SRCH?
These are 2 models of inflation. These are different models of inflation. This is Poisson fluctuation.
Okay.
So what happens is that there are Poisson fluctuations. So the Poisson fluctuation signal is actually plotted here to show that in principle Poisson fluctuations happen because the H1, in these class of models, what actually happens is the power is so much that you can have, so you notice we have only plotted up to redshift of 30.
Yep.
So this is going up, right? Right, this is going up.
Yes.
So the point is, this is actually something where the power can be dramatically more at small scales.
Okay.
When the power is dramatically more at small scales, you can have collapse of structures very early on. Right? These structures will capture what? These are very small structures. They will capture H1. So the idea is that I am looking for H1 from the underlying density field, which is continuous. But then from the formation of these structures, you have discrete objects. You will have Poisson fluctuation in addition because of the discreteness. So fraction of H1 is in this discrete object, right? So one has to show that to be able to tell this dip, right, it should not it should still, the Poisson fluctuations should be small. But I can show that ratio 27 for bispectrum, for instance, which I have not shown, Poisson fluctuation completely wipe out that signal.
And this dip is around this dwarf galaxy region, right, where we do not find much dwarf, 5 megaparsec inverse or something like that.
Oh, this dip is designed so that it meets all the major requirements of the all the large scale structure observation. Okay. So by the way, 5 is chosen because 5 is where Lyman alpha data is. Okay, Lyman alpha probes are not very sensitive. One could have gone a little, we discussed it, but that is why it has been picked. 5 has been picked based on that. Yeah, it is roughly the gene scale in the intergalactic medium at redshift of 3. That's what 5 is. It's around 10 power 9 solar masses. Yeah, it's smaller than dark dwarf galaxy actually.
Okay,
it's even smaller than that.
Thanks. Okay, we have another question.
So you had mentioned 3 techniques for statistical detection of the neutral hydrogen signal, stacking, cross correlation and auto correlation. Are these also useful for detecting the inhomogeneities or only the global signal?
Both. So the whole point is stacking as a technique, like can only see all of these with discrete objects. First you understand, like these are with, some of them are with discrete objects, right? Stacking only works with discrete objects, and it's a technique just for detection. It doesn't have any bearing on the inhomogeneity, right? You have objects and then you stack them. Cross correlation, what are you cross correlating? You're cross correlating brightness temperature with the underlying field, right? So this cross correlation gives you information about how the large scale structure is distributed. So it is a probe of inhomogeneities, right? And that is why we could actually do it with n-body simulation. This one actually captures it. Wait a second. This one. So basically this is like not entirely straightforward plot. So you actually take different brightness temperature of a single halo and you cross correlate it with the underlying density field. So that is why this behavior as a function of R, right, is an indication of the clustering scales of that underlying field. So it is indeed a probe of the underlying distribution, right? But it is linear in the H1 flux because what you are cross correlating an intensity of H1 light with an underlying density field which is dimensionless. The third one, which is the autocorrelation, is a fairly straightforward thing, right? What you do is you measure brightness at one point, measure brightness at another point, you correlate them and you average, right? This is indeed a probe of the underlying distribution and the clustering of the matter, right? And that is the whole aim of doing it actually. This is the technique one is using at epoch of reionization because one wants to know what the signal, what the inhomogeneities are. So apart from stacking, right, the other two do give you information about the inhomogeneous distribution of matter. Stacking does not. Stacking is just a technique for detecting something, right? But stacking has the highest signal to noise as compared to any of the other two techniques, which I did not show, of course, because it uses all the information that there is there to use. Okay, so it will always give you the highest signal to noise. So first you want to stack and see if you succeed, right? But by the way, stacking only works if you know where the object is located. It doesn't work otherwise. Autocorrelation will work anyway, right? Because the signal is statistically homogeneous. That's all you use actually in autocorrelation. Stacking works under special conditions. So stacking can't be used to detect UR. Because I don't know where the signal is, right? But it can work at low redshift when I know, optically I've identified this galaxy, there is H1 in it, I can't detect it individually, right? But I can know 100 galaxies, which I know where they're located, so I can actually co-add them. And says, okay, fine, now I can see if I find it. So they have different like areas of like applicability. I hope I've answered your question.
Yes, sir.
Thank you.
Okay, so if there are no other